there is almost no water here. Only red rock pale sand, dry mountains, and a coastline where the Red Sea stretches toward the horizon in shimmering heat. And yet, Saudi Arabia is building a water system in this landscape that is supposed to supply an entirely new region. Homes, industry, agriculture, construction, all of it, in a place that offers almost none of what a normal water system needs to exist. The strange part is where the water begins.
In a place this dry, the source of the water is the last place you would expect.
It does not begin in a river. There is no great underground reservoir waiting beneath the desert. It begins in the sea. Seawater is drawn from the Red Sea, stripped of its salt, and pushed hundreds of kilometers through an enormous network of pipes before it is stored, distributed, used, collected again as wastewater, treated, and put back to work. The water is not meant to disappear after a single use. It is meant to keep circulating. And that changes the story completely, because Saudi Arabia is not simply building a pipeline into the desert. It is attempting to manufacture an artificial water cycle. This is the water infrastructure being developed for NEOM in northwest Saudi Arabia. The region spans coastal areas, open desert, and mountainous terrain, and every one of those environments needs water despite sitting in one of the most water-scarce regions on the planet. NEOM's stated strategy rests on four connected ideas: desalination, recycling, resource recovery, and digitally managed distribution. More than 250 kilometers of water transmission pipelines have already been laid, according to the company, alongside 27 completed pieces of supporting infrastructure covering transmission, storage, distribution, and recycling. But those numbers only describe the scale. They do not describe the real problem underneath it. Because once you decide to create a large urban region in a desert, almost everything becomes downstream of water. Homes need it. Hotels need it. Factories need it. Construction sites need it. Landscape public spaces need it. And whatever agriculture the region hopes to sustain needs it too. In a landscape with almost no natural fresh water, that dependency becomes the defining constraint on everything built around it. So where does all of that water come from? The answer starts at the coast. Imagine a massive desalination plant sitting between the Red Sea and the desert. Seawater enters the system, but seawater is not drinking water.
The ocean already contains the water. The difficult part is taking everything else out.
It contains dissolved salts and minerals that have to be physically separated from the water itself. The core technology is reverse osmosis. Instead of boiling an ocean and collecting the steam, seawater is forced under intense pressure through specialized membranes. Water molecules pass through. Most dissolved salts do not. The process works by applying pressure strong enough to overcome the natural force of osmosis, pushing water through the membrane in the opposite direction from where it would normally move. It is elegant, but it is not effortless. That pressure requires energy, and the Red Sea creates another complication. It is saltier than the global ocean average, commonly measured around 40 parts of salt per thousand compared with roughly 35 for the world's oceans. High evaporation, limited rainfall, and the sea's relatively restricted connection to the wider Indian Ocean system all contribute to that concentration. So every cubic meter of freshwater requires a difficult separation process in a particularly salty environment. On one side of the membrane, freshwater emerges. On the other, a smaller volume of much more concentrated seawater remains, brine. And that creates one of desalination's biggest problems.
Every liter of fresh water leaves something behind.
Making fresh water is only half the job. You also have to decide what happens to everything you removed. NEOM says its planned desalination system will combine reverse osmosis with hybrid technologies, beginning with a first stage capacity of roughly 333,000 cubic meters of fresh water per day and targeting up to 1 million cubic meters per day at full development. The company also says the system is designed for more than 60% recovery and will be integrated with brine processing facilities. That final part matters. Instead of treating concentrated brine purely as waste, NEOM describes it as another potential resource stream. The idea is to recover valuable minerals and chemical compounds from the concentrate before dealing with whatever remains. So the plant has to solve two problems at once. Produce clean water on one side, manage or potentially exploit an extremely salty byproduct on the other. But making freshwater only solves half the challenge. Now the water has to travel.
Making the water is one challenge. Getting it across this landscape is another.
And this is where the physical scale of the project becomes difficult to imagine. The transmission network is designed to stretch for roughly 600 kilometers. It uses large diameter carbon steel pipes with internal diameters ranging from around 700 millimeters to as much as 200 millimeters. At the largest end, the pipe is wide enough for a person to stand inside. Now multiply one section by thousands. Weld those sections into continuous runs. Bury much of the network beneath the desert. Protect it. Pressurize it. Monitor it, maintain it, and send water through a landscape where extreme heat, dust, distance, and changing terrain are all part of the engineering problem. Some of those routes have to climb toward mountain areas. Water does not naturally want to do that, so pumping stations have to physically lift it against gravity. The planned network can involve as many as 20 pumping stations, and suddenly a pipeline stops looking like a passive object. It becomes a machine stretched across an entire region.
At this scale, the pipeline isn't infrastructure you simply build and forget. It has to think, respond, and survive.
A pipeline section lying beside a construction road can look almost ordinary. But buried beneath the landscape is a system that has to remain reliable for decades. Carbon steel can corrode over time, particularly underground. That means buried sections may require cathodic protection, an electrical system designed to make the pipeline less reactive while allowing more sacrificial materials to take the corrosion instead. None of that appears in the dramatic renderings, but it determines whether the system survives. And the system does not necessarily fail in some spectacular Hollywood moment. It can fail quietly, a slow leak losing pressure over weeks, a pump operating outside its efficient range, a valve that does not completely seal, a small problem that remains invisible until it becomes a large one. That is why NEOM describes its water infrastructure as a connected digital network. Pressure sensors, flow measurements, automated controls, storage monitoring, real-time or near real-time information. The goal is not only to discover failures after they happen. It is to detect abnormal patterns early enough to intervene before a problem becomes expensive. That turns the pipeline network into something much closer to a distributed nervous system than a passive conduit. Water moves. Sensors watch it. Pumps respond. Storage levels change. Demand rises and falls. And software attempts to keep the entire system in balance. But even that creates another problem. Demand is not uniform. A coastal tourism district does not use water in exactly the same way as an inland industrial site. A mountain settlement does not have the same demand profile as a residential district. Hotels can experience seasonal spikes. Industry may need a flatter, more continuous supply. Residential demand rises and falls throughout the day. If the system is designed for one uniform pattern, it either becomes massively oversized or becomes vulnerable when several demand peaks happen at the same time. So the digital layer is not simply there to display information. It is there to balance the physical network. And then there is storage. NEOM's plan includes 6 major reservoirs with a combined capacity of around 6 million cubic meters. That gives the network something every large water system needs: time. Because the desert does not care about your supply schedule. A construction site can suddenly need more water. A desalination unit can go offline. A pump can require maintenance. Demand tomorrow can be higher than demand today. Storage gives the network breathing room. It turns water supply from a simple production line into something closer to a managed reserve. But storage creates its own problem. Water left exposed beneath a desert sun evaporates. And evaporation does more than reduce the amount of water. It can concentrate the salt that remains behind. That is one reason covered or protected storage becomes an important part of the calculation. There is little logic in producing freshwater through an energy-intensive process and then allowing a meaningful portion of it to disappear before it ever reaches a user. But even after the water arrives, the cycle is not finished.
A city doesn't make water disappear. It changes what the water becomes.
Because a city does not simply consume water, it transforms it. What goes down a drain or through an industrial process eventually becomes wastewater. And if that wastewater is discharged and lost, the supposed cycle becomes a one-way system. NEOM's stated strategy moves in the opposite direction. Collect the wastewater, treat it, recover the water, reuse it. The company describes a goal of collecting and treating 100% of wastewater with planned treatment capacity of roughly 250,000 cubic meters per day for an estimated population beyond 1 million people. That system would be supported by around 500 kilometers of sewage collection infrastructure. The principle is simple. Fresh water enters the region. People and industry use it. Wastewater is collected rather than simply discarded. Treatment plants recover water. That recovered water can return to irrigation, landscaping, construction, and potentially industrial uses. And then another layer appears. The wastewater itself contains more than water. It contains organic material, nutrients, biosolids, potentially useful energy. NEOM's public plans describe resource recovery from these waste streams, including nutrient recovery and biogas production. One established method is anaerobic digestion. Bacteria break down organic material without oxygen. The process creates biogas. That gas can be captured and used for energy. The remaining nutrient-rich material can potentially be processed into fertilizer instead of simply becoming waste. None of these technologies are completely new. What is unusual is the intention to integrate them into a new regional water system from the beginning. That is the larger idea. The system is not supposed to have one resource stream and several waste streams. It is supposed to keep converting one into another. And there is already a smaller example inside NEOM. The Al-Bada water recycling plant has a design operational capacity of about 10,000 cubic meters per day. NEOM reports that 98% of the recycled water from the facility is currently being reused, primarily for regreening activities in the surrounding area. That detail matters, because the full system is still the big question. The 6 million cubic meter storage network, the hundreds of kilometers of transmission pipe, the future million cubic meter per day desalination target, the brine processing facilities, the huge wastewater collection system. Those are plans and infrastructure under development. Al-Bada is different. It already exists. It is already producing recycled water, and it is already putting much of that water back into useful applications. That is the part of the story that can actually be tested. Not whether the diagram looks impressive, whether the loop works, and every stage of the larger system exists because the landscape offers almost no margin for error. Not in a sea that begins saltier than most oceans. Not under a sun that punishes exposed water with evaporation. Not across mountain terrain where pipelines must overcome gravity. And not inside a network where every pump, valve, sensor, membrane, and treatment process has to work together. Then there is the energy question. Desalination consumes energy. Pumping water hundreds of kilometers consumes energy. Lifting it toward higher elevations consumes even more. Wastewater treatment consumes energy. And the larger the network becomes, the more important efficiency becomes. That is why NEOM connects its water strategy to renewable energy. The stated model is to use renewable power for desalination and integrate the water system into a broader low-carbon infrastructure design. The concept is almost perfectly circular. Renewable electricity helps make freshwater. Freshwater supports communities and industry. Wastewater is collected. Water is recovered. Resources are extracted. Recovered water is reused. And the system attempts to avoid building the region around continued dependence on groundwater extraction. But elegant systems are still vulnerable systems. Membranes require maintenance. Pumps wear. Pipes age. Storage requires capacity. Demand can exceed assumptions. Digital monitoring cannot eliminate physical failure. And the Red Sea remains a real marine ecosystem rather than an unlimited industrial reservoir. That is why the environmental claims around the project matter. NEOM says its desalination approach aims to minimize marine impacts, process brine, and ultimately pursue a zero, liquid, discharge model at the desalination facility. Whether the full system can achieve everything being targeted is something that can only be demonstrated through operation. Not renderings. Not announcements. Operation. Because the real challenge is no longer simply making fresh water, it is making the entire system work together. Desalination, transmissions, pumping, digital monitoring, wastewater treatment, recycling, resource recovery, renewable energy. Each one is a major engineering problem on its own. Connected together, they become something different. A manufactured water cycle. And that idea may be more important than NEOM itself. Because the problem Saudi Arabia is confronting is not unique to Saudi Arabia. More people, more cities. Hotter climates, greater pressure on rivers and groundwater, less certainty about traditional freshwater supplies. The technologies already exist in pieces. Reverse osmosis exists, large pipelines exist, water recycling exists, digital monitoring exists, renewable energy exists. The difficult part is connecting all of them without creating another problem somewhere else. That is what makes this experiment worth watching.
The technology isn't the mystery anymore. The question is whether all of it can work together.
Saudi Arabia is not trying to make the desert receive more rain. It is trying to make the desert independent of rain, not through one machine, not through one pipeline. Through an entire artificial cycle, seawater becomes freshwater. Freshwater becomes wastewater. Wastewater becomes reclaimed water. Waste becomes a resource, and water moves again, and again. From the coast toward the desert, from the desert back into treatment, from treatment into reuse. Until, in theory, far less has to be thrown away. Look across the landscape, and the whole thing can seem almost impossible. The mountains are dry. The desert is still hot. The Red Sea is still salty. But beneath the surface, hundreds of kilometers of steel pipe could be carrying something the landscape has always lacked: water. And that creates the final question. Not whether Saudi Arabia can build the network, but whether it can keep the same drop alive long enough to build a region around it. Can the membranes keep working? Can the pumps keep lifting? Can the pipes keep carrying? Can the recycling plants keep recovering? Can renewable energy keep the system supplied? And can all of those pieces remain efficient when the network reaches the scale being envisioned? Because building a water network in the desert is an engineering achievement.
The real achievement won't be making water once. It'll be keeping the cycle alive.
Building one that wastes almost nothing is a much harder achievement. And if Saudi Arabia manages to make that entire cycle work at scale, the most important thing it may have built will not be the visible city rising above the desert. It will be something far less visible. A system that manufactures, moves, recovers, and reuses the resource that the landscape never intended to give away. The desert will still be there. The mountains will still be dry. The Red Sea will still be salty. But between them, an artificial water cycle will be taking shape. And the question will no longer be whether you can make fresh water in the desert. It will be whether you can keep the same drop alive long enough to build a civilization around it.